Okay, have you ever stopped and wondered if we could just fundamentally change how airplanes fly? I'm not talking about just making them faster or bigger. I mean changing the very physics of how they move through the air. Well, if that's got you curious, you are in the right place. Because today we're talking about a plane that literally bends air to its will.
So take a look at these. These are not your everyday passenger jets, right? With their engines mounted on top of the wings. Aircraft like the Boeing YC-14 here and the NASA QSRA, well, they just look a little strange. But that weird design held the key to solving one of modern aviation's biggest headaches.
And here's the problem. Our airports are totally clogged. We keep building bigger planes that need longer and longer runways, and it's creating these massive traffic jams both in the sky and on the ground. But what if we could just break out of that cycle? What if a fully loaded transport plane could take off from a runway that's just a fraction of the normal length?
Now, this isn't just, an inconvenience. It's a massive economic drain. The entire hub-and-spoke system that our airports use is being pushed to its absolute limits, all because most aircraft simply cannot perform short takeoffs and landings, or eSTOL, as it's known in the industry.
And get this quote really puts it all in perspective. At major airports, you've got these smaller, unused runways just sitting there completely empty, while the main runways are totally gridlocked. We have the space, we just don't have the tech in our commercial fleets to actually use it. And this is where our strange-looking planes come back into the picture.
So the solution these planes were testing was pretty radical, but also really elegant. Instead of just trying to fight against the air, they used the raw power of their jet engines to manipulate it in a completely new way. The whole concept is called upper surface blowing.
With upper surface blowing, or USB for short, you literally mount the engines on top of the wings. Now, the high-speed exhaust doesn't just push the plane forward. It's directed down and over the wing's big curved flaps. This sheet of super-fast moving air actually sticks to the wing's surface, and it effectively creates a much larger and more powerful lifting surface.
And the results? They are staggering. Seriously, flight testing showed that these USB aircraft can produce a maximal lift coefficient, which is the key measure of a wing's lifting power, of nearly 10. Now, to put that in perspective, a conventional wing is somewhere around a 1 or a 2. This is a total game-changing leap in performance. It allows for incredibly short takeoffs and really steep, quiet landings.
So how in the world does a blast of jet exhaust just magically stick to a wing like that? Well, it's not magic. It's actually a fascinating bit of physics that you've probably seen in your own kitchen sink. It's called the Coanda effect.
The Coanda effect basically just describes how a stream of fluid, and that can be air or water, will want to follow a curved surface. So, if you hold the back of a spoon under a running tap, you'll see the water wrap right around the curve instead of just falling straight down. That's it. USB technology uses that exact same principle, just with a jet engine's exhaust and a giant airplane wing.
This graph really shows the magic at work here. That blue line, that's the lift you'd normally get from a wing. Pretty standard. But look at that red line. That's the massive boost you get with this technology. It's kind of like a 2-for-1 deal. The jet blast physically pushes down on the back of the wing while also creating this powerful suction effect over the top. And both of those forces combine to create that incredible lift we were talking about.
So, we've got this amazing concept, and the physics is proven to work. The problem was, for decades, engineers really struggled to design with it. I mean, you can't build a billion-dollar airplane based on a gut feeling, right? You need models that can accurately predict how it's going to perform. And that's exactly where they hit a wall.
The problem was a classic Goldilocks dilemma. The design tools they had were either too hot or too cold. On one hand, you had these low-fidelity models. They were fast, sure, but they were pretty inaccurate because they couldn't really account for the complex ways the jet and the wing surface interact. And on the other hand, you had high-fidelity computational fluid dynamics. Super accurate, but they took weeks to run a single simulation. Way too complex for the early design stages.
And this isn't some small issue. Think about this for a second. A staggering 90% of a product's final cost is locked in during that first 10% of the design process. If you don't have good, fast, and reliable tools right at the beginning, a revolutionary idea like USB, it's just never going to get off the drawing board.
And that is the breakthrough at the very heart of our source material today. Researchers developed a new methodology that was, you guessed it, just right. It was a model that was both fast enough for initial design work and accurate enough to actually be trusted.
So how'd they crack the code? Well, the genius was in combining old ideas with new ones.
They took the existing fast models and then they layered on two crucial corrections. One, to account for how the jet sucks in or entrains the air around it, and a brand new method to predict the forces of that air as it bends over the wing. It was the perfect mix of speed and accuracy.
And here it is. This is the aha moment. On the left, you see the messy, chaotic, real-world airflow. It's almost impossible to calculate quickly. But on the right, that's the model's elegant solution. It simplifies all that chaos into a single, predictable vortex, which is much, much easier to work with mathematically.
Now, this all sounds great in theory, but the billion-dollar question is, does it actually work in the real world? Well, let's take a look at the data.
The proof is right here in the numbers. This table compares the lift coefficient, that CL value, from actual flight test experiments with the predictions from this new model. And just look how close they are. At a 15-degree angle of attack, the prediction is spot on, perfect. And at every other stage, the new model is within just a few percentage points of reality. This was a massive, massive success.
And that brings us right back to where we started. The data that proved this powerful new design tool worked came from these incredible experimental planes. The theory was finally proven on the actual metal, giving engineers the tool they've been missing to properly design the next generation of short takeoff aircraft.
So, what's the big takeaway here? This technology, this combination of a radical design and a breakthrough predictive model, it really opens up a world of possibilities. Shorter runways mean less noise, less fuel, and the potential for smaller, more convenient airports closer to where we all live. The question is no longer if we can do it, it's when we'll choose to build this new future of aviation.